Imagine a single eruption so powerful that it outshines more than 10 trillion suns. A blast so intense, it forces astronomers to question their understanding of what black holes can actually do. Light pouring out of darkness, energy exploding from a place that should swallow everything, even hope. That's what happened when telescopes caught sight of an eruption unlike anything seen before, a cosmic outburst reported by LiveScience and based on observations that left even seasoned astrophysicists stunned. The discovery wasn't just surprising, it was unsettling. It suggested that black holes, the quiet monsters we thought we understood, might be capable of far more violent behavior than our theories ever predicted. The eruption came from a supermassive black hole at the center of a distant galaxy, one so far away that its light has traveled across billions of years to reach us. But the message that light carried was unmistakable. Something extraordinary had happened, something that broke records for brightness, duration, and raw, unapologetic power. A flare of energy surged outward, carving through cosmic gas, disturbing the structure of its galaxy, and shining so fiercely that if you replaced our sun with this eruption, Earth would be vaporized instantly. But the real mystery isn't just how bright it was. The real mystery is why it happened at all. Because black holes aren't supposed to erupt like this. They're supposed to be the ultimate consumers. Dark, silent, powerful, but restrained by the laws of physics we've spent decades refining. And yet this eruption brazenly ignored those rules. It roared to life, held its brilliance far longer than expected, and behaved in ways that forced scientists to rethink the mechanics of feeding, accretion, jets, and cosmic outbursts. To understand how this happened, you have to imagine the environment around a supermassive black hole. It's not a peaceful place. Gas spirals inward at extreme temperatures, magnetic fields twist into impossible shapes, and deep inside, the event horizon waits like an executioner's blade. Most black holes flicker, brighten, and dim as they feed. But this eruption was something else, something bigger. A jet of energy, possibly triggered by a sudden rush of infalling matter, blasted outward at speeds approaching light. The energy mixed with gas clouds, collided with interstellar material, and released radiation that telescopes eventually captured as a growing bubble of cosmic fire. For months, then years, astronomers watched. Instead of fading like normal eruptions, the brightness held on. It stayed luminous. It refused to die down. Every model said it should have collapsed, but it kept going. It was like watching a match burn underwater, something impossible yet undeniably happening. This eruption isn't just a record breaker, it's a warning sign that the universe still hides mechanisms we don't fully understand. Some theories suggest it might have been triggered by an enormous cloud of gas getting shredded. Others propose a star wandered too close and got annihilated. But even those explanations struggled to match the details. Black holes can tear stars apart, yes, but they don't usually create eruptions this bright, this enduring, or this efficient at turning matter into light. And so, the eruption stands as a challenge. A bright, screaming reminder that the universe is bigger, stranger, and more dangerous than our equations can currently capture. It forces scientists to reconsider how black holes feed, how jets are formed, and how energy moves through galaxies. And as telescopes continue watching, they're uncovering clues that suggest this might only be the beginning. The question isn't whether black holes can create eruptions like this. The question is how many have happened before, and how many more are waiting in the dark, ready to rewrite what we think we know. Billions of light years from Earth, buried inside a galaxy whose starlight began its journey long before humans existed, sits the supermassive black hole responsible for the eruption. It's a behemoth, millions or even billions of times more massive than the Sun, lurking at the galaxy's center like something ancient and coiled. Most galaxies host such giants, quietly influencing stars, gas, and the very shape of their cosmic neighborhoods. But not all of them erupt, and almost none of them erupt like this. To understand the scale of the event, picture the Milky Way. Our galaxy is serene by comparison. Its central black hole, Sagittarius A, is practically sleepy. Occasionally it flickers, but rarely does it surprise astronomers with real drama. The black hole behind the eruption, however, is the opposite. It's more active, more volatile, more aggressively feeding on anything unlucky enough to wander close. And when matter approaches a supermassive black hole at high velocity, the result is a violent dance of physics pushed to its limits. Around the black hole lies the accretion disk, a swirling furnace made of superheated gas, radiation, and magnetic chaos. Regions of this disk can reach millions of degrees. Light bends, space curves, particles slam into one another with energies no human-made particle accelerator could achieve. In most cases, this environment shines brightly but behaves predictably. But something changed. Something added fuel, pressure, or instability to the system. That's when the eruption began. Scientists studying the event noticed that the eruption wasn't a sudden spike of brightness, like a star being torn apart. Instead, it looked like an enormous bubble expanding over time, stretching millions of light-years across. This suggested the eruption wasn't a moment, but a process, a long, sustained release of energy. Something kept feeding the black hole in a steady, unstoppable flow. One hypothesis suggests the galaxy collided with a smaller galaxy, funneling rivers of gas toward its central black hole. Another possibility involves a massive molecular cloud drifting too close and getting devoured. Whatever the trigger was, the response was explosive. Jets of relativistic particles shot outward, carving tunnels through the galactic medium. Shock waves rippled across interstellar space. Gas clouds lit up like lanterns as the jet plowed through them, turning the surrounding region into a cosmic battlefield. Every telescope trained on the event revealed something new. Optical observatories showed glowing filaments stretching like cosmic scars. Infrared instruments detected regions heated by the shock waves. Radio telescopes traced the structure of the expanding bubble. And all the data pointed to the same conclusion. This was one of the most powerful eruptions ever seen. Yet, for all its ferocity, the black hole remains calm at its center. A quiet executioner surrounded by chaos of its own making. The eruption shows us not just the violence black holes are capable of, but the delicate balance that keeps them active. Too little fuel, and they fade. Too much, and they ignite. But in the perfect storm of conditions, they can unleash energies that rival the birth of stars. This distant black hole reminds us that galaxies are not peaceful islands of stars. They are dynamic, evolving systems shaped by cooperation and conflict, growth and destruction. And sometimes, when conditions align, they produce events that echo across cosmic time, reaching us as faint but undeniable signatures of unimaginable power. The eruption didn't just light up the galaxy, it reshaped it. When a black hole unleashes energy on this scale, it becomes an architect of destruction and creation. The shockwave blasted outward, pushing aside gas clouds, compressing some regions while stripping others bare. Entire star-forming nurseries were disrupted. either ignited into bursts of new stars or torn apart before they ever had the chance to begin. Imagine watching a detonation ripple through a city. Buildings collapse, streets twist, debris flies. But some areas, under just the right pressure, become fertile ground for new growth. That's what happened here, except the city was a galaxy, and the blast front stretched across tens of thousands of light years. The eruption carved a massive cavity, an expanding cosmic bubble visible in radio images, glowing with the remnants of energy that had traveled from deep inside the black hole's accretion ring. This bubble wasn't just large, it was expanding faster and glowing brighter than any similar structure astronomers had studied. Normally, these bubbles fade as energy disperses, but this one stayed luminous, as if it kept receiving fresh injections of power from the black hole's core. That persistence puzzled researchers. It implied a sustained mechanism, not a brief catastrophic event. Inside the bubble, particles moved near light speed, guided by magnetic fields twisted by the jet. These magnetic fields shaped the bubble's edges, sharpening some regions while diffusing others bare. The result was an enormous, asymmetrical structure, part shell, part plume, broadcasting its presence across multiple wavelengths. It wasn't just a passive afterglow, it was an active, growing feature. The shock wave also told a story about the jet itself. Jets aren't smooth beams. They flicker, wobble, pulse. This jet left imprints of those variations in the bubble's structure. Ripples indicated moments when the flow strengthened or weakened. Curved edges suggested the jet may have shifted direction slightly, like a fire hose being nudged from one angle to another. These details helped scientists reconstruct a timeline, understanding when the black hole accelerated its feeding and when it momentarily relaxed. What made this eruption especially remarkable was the balance it struck. Too violent, and the jet would have blown past the galaxy's edges, losing energy into intergalactic space. Too weak, and the bubble would have collapsed before reaching the size we observe. Instead, conditions aligned perfectly to create a colossal, long-lasting monument to the black hole's outburst. What's even more astonishing is the distance at which this event occurred. The galaxy lies billions of light years away, meaning everything we're observing today happened long before Earth existed. The shockwave may have finished expanding eons ago, yet the light only now reaches us, like a ghostly record of a cosmic upheaval frozen in time. This eruption invites a deeper question. How often do such events reshape galaxies? We've seen similar structures closer to home, like the Fermi bubbles emerging from the Milky Way's center. These enormous lobes of gamma-ray energy hint that our own galaxy might have experienced a comparable eruption millions of years ago. If so, we're living in the quiet aftermath of a much older blast. In that light, the record-breaking eruption isn't just an isolated occurrence. It's part of a larger pattern in the life cycle of galaxies, periods of calm punctuated by violent awakenings. These eruptions regulate star formation, redistribute matter, and influence the future of entire stellar populations. They act as engines of change, ensuring galaxies don't stagnate. And in this cosmic symphony of creation and destruction, black holes are the conductors, shaping their surroundings with forces beyond anything we experience in daily life. This eruption is a reminder that galaxies aren't static. They grow, evolve, and erupt in long, dramatic cycles, driven by the dark hearts at their centers. To grasp the brightness of this eruption, imagine gathering 10 trillion suns into a single point, all shining at once, all focused into one enormous flare. Now imagine that this burst of brilliance outshines them, not for minutes, not for hours, but for months and years. That is the scale of the light produced by the black hole's eruption. Brightness in astronomy isn't just about how much light something emits. It's about how efficiently energy transforms into radiation. Most cosmic events are inefficient. Only a small fraction of energy becomes visible light or detectable signals. But this eruption broke the trend. It radiated with incredible efficiency, meaning an enormous portion of the energy generated actually escaped into the galaxy instead of being swallowed or dissipated. To generate that kind of luminosity, matter had to fall into the black hole at an astonishing rate. Picture a river of gas spiraling inward, fragments of stars, dust, plasma, all of it drawn into the gravitational well. As it swirls around the event horizon, friction and magnetic interactions heat it to mind-crushing temperatures. Those temperatures ignite radiation across the electromagnetic spectrum: radio waves, X-rays, gamma rays, ultraviolet bursts, and visible light. Normally, these emissions are sporadic, spiking when the black hole gets an extra gulp of material. But this eruption sustained its glow. It was as if the black hole had tapped into a reservoir of matter so vast that it could feed continuously without interruption. The efficiency of this process puzzled astronomers because supermassive black holes usually self-regulate. When the accretion disk gets too hot or too bright, it pushes away incoming matter, starving itself until the environment calms. It's a natural feedback loop. But this eruption defied that mechanism. It kept intensifying without showing signs of self-limitation. Instead of shutting down the inflow, it encouraged it. Energy surged outward, yet matter continued to fall in. It was a feedback loop in reverse, each surge pulling in more fuel, each flare triggering an even bigger one. That's why the eruption didn't fade the way most cosmic outbursts do. It was sustained, relentless, and self-reinforcing. What makes this brightness even more astonishing is the distance. Because the galaxy is so far away, the light we see now has stretched and weakened as the universe expanded. The eruption was far brighter in its original form, bright enough to outshine its entire host galaxy. At its peak, the eruption would have been visible from neighboring galaxies like a beacon, announcing its presence across intergalactic space. Even today, billions of years later, we can see the evidence. Telescopes detect the residual glow in radio waves, infrared emissions, and X-ray echoes. These signals show that the eruption wasn't just a momentary flare, it was a sustained transformation of the black hole's environment. And this leads to an even bigger question. If this eruption was so bright that we can still detect its afterglow across billions of light years, how many others have we missed? How many eruptions occurred before we had telescopes tuned to detect them? How many galaxies have been reshaped by invisible blasts we might never see? Brightness isn't just a measure of energy, it's a window into the past. This eruption, shining with the intensity of 10 trillion suns, is a message from a bygone era, telling us that the universe is far more dynamic, far more violent, and far more unpredictable than we once believed. Something must have fed the black hole enough fuel to ignite an eruption of this magnitude. And one of the most compelling theories is also one of the most tragic: a star wandering too close. Stars stray all the time in chaotic galactic centers, pulled by gravitational tides that mix them into unpredictable orbits. Most pass safely, but every so often, one drifts too close to a supermassive black hole and meets a violent end. If a star approached this black hole at just the wrong angle, tidal forces would have torn it apart long before it reached the event horizon. This process, known as a tidal disruption event, stretches the star into a stream of gas, like cosmic spaghetti, and flings part of it outward, while the rest spirals inward. For most black holes, this results in a brief flare lasting weeks or months. Powerful, yes, but nothing compared to the years-long eruption captured in this event. Yet this particular star might have been different. It could have been a giant, massive, expansive, and rich with material. When shredded, it would have produced an enormous river of gas, enough to overwhelm the black hole's usual self-regulating mechanisms. The inflow may have been so dense, so sustained, that the black hole entered a rare state of overfeeding, generating energy at a rate it normally cannot maintain. Astronomers studying the light curve of the eruption noticed something intriguing. The brightness rose in a pattern consistent with a huge influx of material, not a sudden collision. This favored the idea of a star, or perhaps even multiple stars, being consumed in sequence. If the black hole resided in a chaotic stellar environment, say after a galactic merger, it might have encountered multiple victims in a short period of time. As the shredded star's material spiraled inward, the magnetic fields around the black hole twisted tighter. These magnetic knots acted like slingshots, accelerating particles and energizing the emerging jet. When the jet finally burst free, it carried with it the signature of the star's remains. Fragments of gas, stripped of their original form, heated to millions of degrees and hurled outward at nearly the speed of light. If the star had a dense core or unusual chemical composition, that too could have altered the jet's behavior. Some stars contain highly magnetized regions. Others hold unusually thick layers of helium or carbon. These differences affect how the material breaks apart, how it falls inward, and how efficiently it produces radiation. In this scenario, the star didn't just die. It became the fuel for one of the brightest eruptions in cosmic history. Its destruction shaped a jet that carved a bubble through the galaxy, illuminated gas clouds, and shined brighter than trillions of suns combined. It became a message carried across billions of years, a silent testament to the violence that unfolds when a massive star strays too close to a supermassive predator. And yet this explanation, dramatic as it is, may not fully capture the event. The eruption lasted too long, too steadily, too efficiently. One star, even a large one, usually doesn't provide material for such an extended eruption. This leads to another possibility. The black hole wasn't fed by a single star, but by a chain reaction of events, each one feeding the next. If the galaxy had recently undergone a merger, the central region would have been full of chaos, gas clouds colliding, stars on unstable orbits, debris drifting inward. The black hole could have encountered not one, but many. A star might have triggered the initial flare, but subsequent inflows could have kept the eruption alive, turning a single catastrophe into a sustained cosmic spectacle. Whatever the exact cause, the event shows how fragile the boundary between stability and eruption can be. A single star drifting too close might be all it takes to awaken a black hole and unleash a storm capable of rewriting the structure of an entire galaxy. Black hole jets are among the most mysterious phenomena in astrophysics. We know they exist. We can film them, measure them, track them across millions of light years. But we still don't fully understand how black holes, objects that trap light, can launch jets that travel faster than 99% of the speed of light. In this eruption, the jet behaved in ways that stretched existing theories to their limits. For one, it remained stable far longer than expected. Jets usually flicker like unstable flames. They twist, collapse, reignite, or weaken as the inflow of material changes. But this jet didn't behave like an unstable flame. It acted like a blowtorch, steady, precise, and relentlessly powerful. It carved a path through the galaxy with remarkable consistency, keeping its shape even as it expanded into interstellar gas. This kind of stability suggests something unusual was happening at the event horizon. One theory points to magnetic flux saturation. If magnetic fields around the black hole reached a critical threshold, known as a magnetically arrested disk, the system could maintain extremely high jet power for an extended period. In this state, magnetic pressure partially counters gravity, allowing the black hole to feed at extreme rates without choking off the inflow. Another theory suggests the spin of the black hole played a crucial role. If the black hole was spinning rapidly, a relic of previous mergers or past feeding frenzies, it could tap into rotational energy through a process known as the Blandford's-Nogic mechanism. This mechanism effectively turns the black hole into a cosmic dynamo, converting rotational energy into outward jet power. A faster spin means a more powerful jet. And if this black hole was spinning near the theoretical maximum, the eruption could sustain itself at levels previously thought improbable. In this event, the jet didn't just break records, it broke expectations. It showed traits of extreme collimation, meaning it stayed tightly focused rather than spreading out. This focus kept its energy concentrated, allowing it to bore into surrounding gas like a drill. It also maintained its direction with surprising consistency. Jets often wobble due to instabilities in the accretion disk or fluctuations in magnetic fields, but this one remained almost perfectly aligned. This precision implies that the black hole and its disk were in a rare moment of balance, aligned, stable, and feeding in a way that reinforced the jet's structure rather than disrupting it. As the jet extended outward, it inflated the massive bubble observed by telescopes. The bubble's edges show signs of repeated bursts of energy, like layers in a tree trunk. These layers represent episodes in the jet's life, moments of increased power, brief lulls, and surges that reignited the flow. It's a timeline written in gas and radiation. And deep within that timeline lies the most surprising clue. The jet didn't decay the way it should have. Instead of weakening gradually, it held its strength much longer. This suggests that the black hole wasn't just fed, it was overfed. It may have entered a state of runaway consumption, drawing in the material faster than the disk could stabilize it, yet somehow maintaining coherence. Jets like this aren't just rare, they're invaluable. They give scientists a chance to test theories about black hole physics under extreme conditions. They show how magnetic fields shape cosmic structures. They show how energy flows from the smallest scales around the event horizon to the largest scales of intergalactic space. This jet wasn't just powerful, it was a cosmic outlier. Proof that black holes can exceed our expectations in ways we're only beginning to understand. At the heart of this eruption lies a structure so enormous, so bright, and so persistent that it challenged every model astronomers used to predict how black hole outbursts behave. The expanding bubble, an inflated, glowing cavity carved by the jet, grew to a scale that dwarfed its host galaxy's central region. It didn't just push outward, it bulldozed through gas clouds, reshaped magnetic fields, and spread energy across regions that should have been too distant to be affected. What made this bubble so strange wasn't only its size, it was its longevity. Most bubbles produced by black hole jets fade relatively quickly, Energy dilutes, particles slow down, and the structure loses its glow. But this one remained astonishingly bright for an exceptionally long time, as if someone kept reheating it from the inside. Telescopes studying the bubble found that it radiated intensely in radio wavelengths, which meant electrons were accelerating continuously. That's the kind of behavior you expect from a still active jet, not a dying remnant. And the bubble's shape, lopsided, asymmetrical, and sharply defined, suggested that the jet supplying energy had not weakened smoothly, but surged in pulses. Think of it like a heartbeat. Each time the black hole received a rush of new material, the jet strengthened, and the bubble's edges expanded just a little farther, leaving visible ridges. These ridges became a fossil record of the eruption's life cycle. They charted moments of violence and calm, periods where the black hole inhaled deeply and then unleashed another surge of energy. The interior of the bubble was even more revealing. High-energy particles, some traveling faster than 99.9% of the speed of light, bounced through the cavity, trapped by magnetic loops. These loops behaved like cosmic trampolines, keeping the particles energized far longer than expected. That helped explain the bubble's brightness. It wasn't just glowing from the original eruption, it was being actively maintained by a chaotic internal storm of charged particles and fluctuating magnetic fields. What really surprised scientists was how the bubble's structure compared with similar features in other galaxies. The Milky Way has its own giant structures, the Fermi bubbles, believed to be remnants of an ancient eruption from Sagittarius A star. But those bubbles are far more diffuse. They're old, faded relics. The bubble created by this eruption was crisp, vibrant, and freshly carved, like graffiti still dripping with paint. The difference revealed something important. This eruption was not just a powerful blast, it was a rare configuration of conditions that allowed a black hole to sustain an outburst far beyond typical limits. The inflow must have been massive, the magnetic fields must have been tuned perfectly, and the environment around the black hole must have offered just enough resistance to shape the bubble without tearing it apart. Even more fascinating was the bubble's interaction with the galaxy's gas. In some regions, the gas had compressed so intensely that it might eventually collapse into new stars. In others, gas had been blown away completely, leaving star-forming regions barren. These competing processes meant the eruption could jumpstart star formation in some parts of the galaxy while shutting it down in others, a dual role that black holes often play as both creators and destroyers. This cosmic bubble wasn't just an artifact, it was a map of the galaxy's future. It showed where stars might form, where they might fail to form, and how the galaxy's evolution had been permanently altered by the black hole's violent awakening. And as astronomers traced the edges of the bubble, they found something that made the event even more extraordinary. The bubble was still expanding. Slowly, yes, but unmistakably. The eruption had ended long ago, yet its fingerprints continued to travel outward, carrying the echo of an event so powerful it would reshape the galaxy for millions of years to come. To produce an eruption this extreme, a black hole must enter a feeding state far beyond anything typically observed, not just steady accretion, not just episodic bursts. This was more like a feeding frenzy, an overwhelming flood of matter spiraling inward so quickly that the black hole's usual self-regulating mechanisms failed. Black holes don't always eat efficiently. In fact, most of the material that approaches a black hole never reaches the event horizon. It heats up, emits radiation, and gets pushed away by the pressure of its own emissions. This balance keeps black holes from growing uncontrollably. But when a massive flow of material arrives all at once, the system can destabilize. That's likely what happened here. The black hole didn't just receive a steady supply of food, it received a torrent. Enough gas to overwhelm the feedback loop, enough material to build a gigantic unstable accretion disk glowing with unimaginable heat. In this environment, magnetic fields twisted into chaotic, compressed structures capable of launching jets with immense force. The feeding frenzy also explains the eruption's brightness. When a black hole consumes material at near maximum efficiency, it converts matter into light with astonishing effectiveness. Each particle spiraling inward releases energy through friction, magnetic turbulence, and relativistic motion. The more matter, the more energy. And when matter rushes inward faster than the disk can process, the energy output spikes into the extreme. Yet even this explanation has limits. There's only so much a black hole can eat before the surrounding radiation becomes overwhelming and pushes the rest of the material away. But in this eruption, somehow the inflow wasn't shut down. It continued feeding through conditions that should have choked it off. That's why the event lasted so long. It wasn't a single burst, it was a runaway process. Part of the frenzy may have come from the galaxy's larger environment. If the galaxy had recently merged with another, tidal forces would have funneled enormous amounts of gas toward the center. The black hole would have found itself drowning in material, surrounded by clouds and remnants of disrupted stars. Once the inflow began, it would have been impossible to stop until the reservoir emptied. Another possibility is that the black hole was already spinning rapidly, and the feeding frenzy amplified its rotation even further. A spinning black hole drags space-time around with it, pulling material into tight, fast orbits. This rapid rotation increases the efficiency of accretion, which means every bit of infalling matter produces even more energy than usual. The result is a system spiraling toward a temporary but extreme state, a cosmic supernova of accretion. As the feeding frenzy intensified, the jet strengthened, the bubble expanded, the galaxy trembled under the onslaught, and the black hole, in a strange twist, grew calmer at its center. The region around the event horizon stabilized into a violent equilibrium, a state of perfect chaos where forces normally at war found a temporary alignment. It's a reminder of how complex black holes truly are. They're not simple vacuums sucking in matter. They're dynamic engines powered by gravity, rotation, magnetism, and quantum effects. And when the conditions align just right, they can unleash eruptions that defy everything we expect from the dark giants of the universe. Long after the eruption itself faded, its echoes continued to ripple across the cosmos, faint signals traveling billions of years before brushing the sensors of our telescopes. These echoes came in many forms: radio waves drifting through intergalactic space, X-ray reflections bouncing off distant clouds, infrared signatures glowing from shock-heated dust. Each one acted like a piece of cosmic archaeology, revealing different layers of the eruption's history. Radio observations captured the most striking evidence. They showed enormous lobes of energized particles stretching outward like ghostly wings, still glowing long after the jet had weakened. These lobes served as time capsules. Their size indicated the jet remained active far longer than typical eruptions. Their brightness showed that energy continued circulating inside them long after the initial blast faded, boosted by magnetic turbulence and high-velocity particles that refused to slow. X-ray telescopes found scattered hotspots around the bubble's edges, regions where shock waves struck dense clouds of gas, compressing and heating them to tens of millions of degrees. These hotspots acted like sparks frozen in time, marking the moments when the jet's energy slammed headfirst into the galactic environment. By measuring the temperature and distribution of these X-ray flares, astronomers could reconstruct how quickly the bubble expanded and how much power had driven it. Even in the infrared, where cooler structures dominate, the galaxy showed the eruption's fingerprints. Dust grains heated by the shock wave radiated faint warmth, outlining trails of material pushed aside like cosmic debris. Some regions glowed brighter, suggesting the shockwave compressed gas enough to trigger new waves of star formation. Other regions dimmed, indicating gas had been cleared out entirely, leaving behind hollow pockets where stars might never form again. All these echoes combined to paint a picture of a galaxy profoundly reshaped by a single event. The eruption wasn't a moment, it was a transformation that continued altering its environment long after the initial energy burst had subsided. But the echoes weren't limited to the galaxy that hosted the eruption. Across the vast gulf of space, they also traveled through intergalactic medium, interacting with tenuous filaments of gas stretching between galaxies. In these lonely regions, even a faint whisper of energy can have dramatic effects. High-energy particles from the eruption may have ionized pockets of intergalactic gas, leaving faint detectable imprints. These traces are subtle, almost lost in cosmic noise, but they offer clues about how black hole jets influence the large-scale structure of the universe. In essence, the eruption's echoes show that black holes are far from isolated phenomena. Their effects extend outward, sometimes across distances so vast they defy intuition. A single outburst from a distant galaxy can alter its surroundings for millions of years, shaping both its own future and the broader cosmic landscape. And when those echoes arrive here on Earth, as faint signals in our telescopes, they remind us that we are observers of ancient violence. Every photon, every particle, every pulse of radiation from this eruption began its journey before humans existed, before Earth formed, before the sun ignited. They are messages from a time when the universe was younger, stranger, and more volatile. Studying them isn't just an act of scientific curiosity, it's a way of peering into the universe's past, of seeing how galaxies grew, how black holes evolved, and how cosmic structures formed in the midst of chaos. The echoes teach us that nothing in the universe happens in isolation. Every eruption, no matter how distant, becomes part of a much larger story, weaving itself into the cosmic tapestry that spans billions of years. This eruption wasn't just a spectacle, it was a challenge, a cosmic dare that forced astronomers to question the very foundations of black hole physics. For decades, scientists believed they had a reliable understanding of how black holes feed, how jets form, and how energy escapes from regions where even light cannot. But this event shattered those assumptions. The eruption's extraordinary brightness, longevity, and efficiency revealed cracks in existing theories. It suggested that black holes can convert matter into energy far more effectively than models predicted. It showed that jets can remain stable for years or decades under the right conditions. It demonstrated that galaxy-shaping bubbles can grow far larger and stay luminous far longer than expected. Perhaps most importantly, it proved that black holes are not passive anchors in the centers of galaxies. They are active participants in galaxy evolution, capable of sudden awakenings that transform their surroundings on colossal scales. One of the biggest questions raised by this event is about accretion physics, the process of how matter falls into a black hole. Existing models predicted limits on how quickly black holes could feed, controlled by the so-called Eddington limit. Beyond this point, radiation pressure should push away incoming material. Yet, this eruption blew past those limits, suggesting a loophole. Under the right magnetic and rotational conditions, black holes might feed at super Eddington rates for extended periods. This has enormous implications. If black holes can enter states of extreme accretion more often than previously believed, then their influence on galaxy growth is far more dramatic. They could regulate star formation, strip galaxies of gas, or ignite waves of new stellar births, depending on the timing and intensity of their eruptions. Another puzzle involves jet formation. The jet from this eruption was too stable, too precise, too powerful. That implies the black hole's magnetic fields reached a magnetically arrested disk. If such states are more common than thought, they could explain why some galaxies display massive radio lobes while others do not. Even the shape of the bubble challenges assumptions. Its asymmetry hints at a dynamic environment where the jet interacted with uneven gas distributions, teaching us about the structure of galaxies billions of years ago. The bubble's brightness, meanwhile, hints at a constant stream of energy injection, which requires us to revise models of how long black hole jets can remain active. And the fact that we detected this eruption at all is remarkable. The universe is enormous, and events like these may occur frequently without our knowledge. Our telescopes happen to be pointed at the right place at the right time, catching a moment of cosmic upheaval that had already ended long before life on Earth began. The eruption is a message from the universe, reminding us that our understanding is incomplete. Black holes are not simple, static objects. They're complex engines capable of sudden, unpredictable shifts. They can remain quiet for millions of years and then awaken in an instant, unleashing forces that reshape galaxies and echo across cosmic time. Every discovery like this pushes the frontier of our knowledge further, revealing new mysteries and raising new questions. How often do such eruptions occur? How many jets have carved unseen bubbles in distant galaxies? What triggers the transition from quiet feeding to explosive outburst? And could our own galaxy experience something similar in the far future? The truth is, we're only beginning to understand the deep interplay between black holes and the universe they inhabit. This eruption is not an answer, it's an invitation, a call to keep watching, keep questioning, keep looking deeper into the cosmos. Because as bright as this eruption was, the mysteries it uncovered shine even brighter. When the eruption finally began to fade, the galaxy entered a strange kind of quiet, a hush that followed years of unimaginable violence. But this silence wasn't peaceful. It was the aftermath of transformation, a pause in which the galaxy adjusted to its new structure. The black hole, once blazing with activity, slipped back into a subdued state, its jets dimming, its accretion disk cooling, its furious glow collapsing into something far more ordinary. Yet even in its quiet, the black hole was not the same. A feeding event this enormous doesn't leave a black hole unchanged. It grows. It spins faster. It reshapes the space around it. The mass that the black hole consumed, whether from stars, gas clouds, or debris funneled inward during a galactic merger, became part of its structure. The event horizon expanded, the gravitational pull intensified, and deep inside, the spin, dragged forward by infalling matter, may have approached the maximum allowed by the laws of physics. The galaxy around it felt the silence in different ways. Regions near the center became low-density deserts where gas had been blown apart or pushed outward by the expanding bubble. In these barren pockets, star formation slowed dramatically. Any remaining gas drifted lazily, no longer bound to the structures that once held it together. The very heart of the galaxy had been hollowed out. Farther away, the story changed. Gas compressed by shock waves found new stability, cooling into dense knots that might one day ignite into stars. In these regions, the silence took the form of newfound stillness, a calm that allowed gravity to gather material once scattered by the blast. These were the seeds of future stars, future solar systems, future worlds. In this sense, the eruption was both destructive and creative. It tore apart stellar nurseries near the core, but ignited new ones farther out. Even the stars that survived the eruption were not untouched. Many had been bathed in high-energy radiation. Their outer atmospheres were stripped. Their stellar winds changed. Some stars altered course slightly after the shockwave passed, knocked into new orbits by the sudden movement of gas. Over millions of years, these shifts will reshape the galaxy's spiral arms, subtly reweaving the galactic architecture. And then there was the interstellar dust, tiny grains floating between the stars. Dust is fragile. Shockwaves can destroy it, shattering particles into finer fragments. But dust is also the seed of planets, the building blocks from which worlds form. After the eruption, astronomers suspect some regions of dust were obliterated, while others were compressed into thicker structures. In those regions, dense disks might one day spiral into stars and planets, their origins tied to the violence of this event. As for the black hole, its silence was deceptive. It wasn't done. It never is. Black holes don't sleep. They only wait. Another gas cloud may drift inward someday. Another star may wander too close. Another merger may dump fresh material into its gravitational well. When that happens, the silence could end in an instant, replaced once again by a roar that lights up the cosmos. But for now, the galaxy lives in the long shadow of the eruption, its future subtly rewritten by the blast. The silence after the storm isn't an ending. It's the beginning of a new chapter in the galaxy's evolution, shaped by the scars left behind and the seeds planted by one of the most powerful eruptions ever witnessed. What remains is the memory, a cosmic stillness that carries the echo of ancient violence, preserved in light that traveled billions of years to reach us. It's a reminder that every galaxy, no matter how peaceful it appears, carries a history forged in fire. Long after the final jets weakened, long after the shockwaves spread beyond the reach of telescopes, the legacy of this eruption remained imprinted in the galaxy like scars on ancient stone. Every part of the system carried some reminder of what had happened, some signature etched in gas, dust, magnetic fields, or starlight. These traces became the galaxy's new blueprint, defining how it would evolve for billions of years to come. In the central region, once dense with gas and potential star formation, the eruption left behind a vast cavity. This wasn't just emptiness, it was a controlled emptiness, shaped by an explosion so immense that it carved out space where material had once flowed freely. The cavity's boundaries became a kind of relict monument, gas compressed along the edges, temperature gradients still visible, magnetic fields twisted into strange new arrangements. Astronomers believe that these central cavities can persist for extremely long periods. Without gas to replenish the core, the central black hole may remain in a low accretion state for millions of years. Only when fresh material drifts inward, perhaps from minor mergers or infalling clouds, will the black hole have another chance to awaken. Until then, the memory of its eruption lingers in the empty space around it. But the legacy of the event didn't end at the core. The surrounding galactic disk experienced slower, subtler changes. Stars born from gas compressed by the shockwave carried the imprint of their violent origins. Their initial rotations, chemical compositions, and even their clustering patterns bore traces of the conditions created by the eruption. Some of these stars might have formed in unexpected locations, regions that would never have developed star-forming clouds if not for the pressure of the expanding bubble. Over millions of years, These new stars could drift outward, merging with the galaxy's natural patterns. Other stars, those too close to the eruption's core, might have suffered atmospheric stripping or been nudged into altered orbits. Their trajectories would gradually diverge from the regular motion of the galactic disk, serving as tiny markers of the eruption's influence. Even the galaxy's magnetic fields held on to the eruption's memory. Normally, galactic magnetic fields form intricate spirals shaped by the movement of gas and stars, but the shock waves from the eruption stretched, twisted, and disrupted these fields. The result was a pattern of magnetic turbulence that might take millions of years to settle back into equilibrium. During that time, the altered fields could affect how gas flows through the galaxy, how clouds collapse into stars, and how cosmic rays propagate. This in turn influences the galaxy's long-term evolution. A single eruption, if powerful enough, becomes a defining event in a galaxy's life, like a geological upheaval on a planetary scale. Mountains rise, valleys collapse, rivers change course. Except here, the landscape is stellar and the rivers are streams of gas drifting through interstellar space. Farther out, where the shock wave weakened into a gentle push, gas clouds shifted just enough to change the fate of entire star-forming regions. Some of those clouds, subtly compressed, might form stars centuries or millennia earlier than they otherwise would have. Others, nudged out of alignment, might delay their collapse or even disperse entirely. Over cosmic timescales, these changes accumulate. They alter the galaxy's star formation rate. They reshape spiral arms. They shift the chemical evolution of future generations of stars. And all of it stems from a single eruption, a burst of energy so powerful that its echoes guide the galaxy long after the light has faded. And then there is the final legacy, the message carried across the universe to us. Without meaning to, without intention, the eruption became a cosmic signal. Its light traveled across billions of years, passing ancient nebulae, dead stars, emerging galaxies, the expanding fabric of space-time itself. And eventually, that light reached Earth, whispering a story that unfolded long before our planet formed. In capturing it, studying it, understanding it, we extended the galaxy's legacy even further. Its eruption became part of our scientific heritage, a clue that helps us understand the laws of the universe and the forces that shape galaxies. A black hole erupted, a galaxy changed, and billions of years later, we learned. That is the legacy. Every once in a while, the universe offers a moment of rare clarity. A brief window where something so extreme, so violent, so unthinkably powerful unfolds that it exposes hidden truths about how the cosmos really works. This eruption was one of those moments, a lesson delivered not through equations or theories, but through raw, unfiltered cosmic force. Black holes, for all their mystery, have always been surprisingly consistent. They follow patterns. They display predictable limits. They radiate energy in ways we've charted for decades. But this event broke through those boundaries. It forced astronomers to confront a reality where black holes might be capable of feeding far more efficiently than expected, where jets might sustain their shape and power far longer than standard models allow, where the very architecture of galaxies might depend more heavily on these outbursts than we ever imagined. One of the first secrets revealed was about energy extraction, how black holes convert infalling mass into radiation. The efficiency of this process in the eruption was staggering. It pushed the boundaries of known physics, hinting that in certain extreme conditions, a black hole might extract energy not just from infalling matter, but from its own rotation. If the black hole spun rapidly enough, it could tap into its rotational reservoir, feeding the jet with power drawn directly from the twisting of space-time itself. This idea had been proposed in theory, but no observation had ever suggested it could happen at such an extreme level. Until this eruption. Suddenly, what had long been a theoretical curiosity became a real possibility. Black holes might be capable of draining their own spin to fuel eruptions of incredible magnitude. The eruption also taught us about magnetic fields, those invisible structures that weave through galaxies like cosmic scaffolding. Normally, magnetic fields near black holes are chaotic, tangled, constantly breaking and reforming. But in this event, something extraordinary happened. Magnetic fields aligned, strengthened, and formed a stable configuration capable of channeling energy into a jet that remained focused for years. This was a sign of a magnetically arrested disk, a state that only occurs when magnetic pressure grows so strong it partially halts the flow of gas around the black hole. Astronomers had simulated such states, but they had never conclusively observed one in action. Until this eruption. The clear stability of the jet, the layered structure of the bubble, and the sustained power all pointed to a magnetically arrested disk fueling the blast. Then came the third lesson. Galactic ecosystems are more fragile and more dynamic than we realized. One eruption, one moment of violence from a black hole reshaped the entire galaxy's future. Star formation shut down in some regions and accelerated in others. Gas flows changed direction. Magnetic fields rewired. Structures that took millions of years to form were erased in an instant. This showed scientists something profound, that black holes don't just sit at the centers of galaxies. They sculpt them. They choose where stars form. They decide which regions thrive and which collapse. They set the pace of galactic evolution, not through steady influence, but through sudden, dramatic events that act like cosmic resets. And then there was the fourth lesson, perhaps the most humbling of all. The universe is hiding far more of these eruptions than we've seen. This event was only visible because it happened in the right type of galaxy, at the right angle, at the right time, sending signals directly toward Earth. Countless others may have erupted in directions we cannot observe, or in wavelengths our telescopes cannot detect, or in galaxies too distant or obscured for us to study. The eruption was a reminder that our view of the universe is like peering through a keyhole. We see only what chance allows us to see. And when something this extraordinary slips through the gap, it changes everything. Black holes, once thought of as simple gravitational traps, revealed themselves as engines of unimaginable complexity. Machines that draw on rotation, magnetism, and extreme physics to release energies greater than the combined light of trillions of suns. They are not passive. They are not predictable. They are not silent. They are teachers, offering lessons written in the brightest flares and the deepest shadows. Lessons about power, chaos, creation, destruction, and the fragile balance that holds galaxies together. And every time we catch one in the act, every eruption, every jet, every shockwave, we learn something that reshapes our understanding of the cosmos. This event was one of the great lessons, a rare cosmic lecture delivered across billions of years to anyone who is watching. And now, because we witnessed it, our understanding of black holes and of the universe itself will never be the same. If there's one truth this eruption makes impossible to ignore, it's that the universe is built not on quiet stability, but on violence, on sudden upheavals, on eruptions so enormous they rewrite the structure of galaxies. And while that might sound bleak, it's the very reason the cosmos looks the way it does today. Stars form because old stars explode. Heavy elements exist because giant stellar cores collapse. Planets arise from the rubble of previous generations of stars. Even life, fragile as it is, owes its existence to explosions, collisions, and cosmic catastrophes that happened billions of years before Earth formed. This eruption was just another chapter in that long, violent history. The galaxy in which it occurred didn't evolve through gentle processes. It grew through mergers, through bursts of star formation, through gravitational distortions. And at its center, the black hole played the role of both destroyer and creator. When it erupted, it didn't merely illuminate the galaxy, it sculpted it. It carved cavities, it forged shock waves, it altered the flow of gas that determines where stars can be born. Violence in the universe isn't an accident, it's a feature, a mechanism, a tool that nature uses to build structure from chaos. Galaxies themselves are shaped by encounters that appear violent beyond comprehension. They collide, merge, tear each other apart. Their stars crash together in tides of gravitational force. And through these interactions, new galaxies are born, bigger, brighter, more complex. In this larger context, the eruption becomes part of a cosmic cycle that plays out repeatedly across billions of years. But what makes this event so compelling is not just its scale, but its timing. It happened when the universe was still relatively young. Galaxies were forming rapidly. Black holes were growing even faster. Everything was more chaotic, more energetic. Conditions were ripe for colossal eruptions, yet only a fraction of them have left visible traces. Most faded into silence long before their light reached us. This eruption reminds us that even the calmest-looking galaxies may have violent pasts. A galaxy today can appear serene, its stars orbiting in smooth spirals, its black hole quiet and unassuming. But look beneath the surface. Study its gas distribution, its magnetic fields, its stellar populations, and you'll find fingerprints of ancient upheavals, cavities carved by jets, disrupted arms, pockets of stars born from compressed gas. In this sense, the cosmos resembles a battlefield long after the fighting has ended. The war is over, but the landscape still bears scars. Even the Milky Way carries evidence of ancient violence. The Fermi bubbles, those vast gamma-ray structures ballooning from its center, are relics of an eruption millions of years old. They hint that our own black hole once awakened, feeding on a sudden influx of matter and unleashing jets that lit up the galaxy. For us, that event is merely a historical curiosity. For life on Earth, which formed much later, it had no direct effect. But for the galaxy as a whole, it was transformative. The eruption described in the LiveScience report is a far more extreme example of the same cosmic behavior. It shows us what can happen when all the conditions align: a plentiful supply of gas, a fast-spinning black hole, and magnetic fields twisted into a perfect storm. And it forces us to rethink how common such transformations might be. If this event occurred in a distant galaxy billions of years ago, how many others happened around the same time? How many shaped the galaxies we see today? How many influenced the formation of planets, the distribution of elements, the very architecture of the universe? Violence, in cosmic terms, is creation. It's the chisel carving the structure of galaxies. It's the hammer forging stars. It's the spark that ignites the next stage of evolution. This eruption didn't merely brighten the universe for a moment, it helped build it. And somewhere, deep inside the region where the blast once raged, the black hole waits. Quiet for now, resting, but not finished. Because in a universe built on violence, silence is only ever temporary.
Every photon from this eruption is a traveler,
an ancient messenger that began its journey long before Earth existed, long before the sun ignited, long before the Milky Way finished assembling its spiral arms. When we observe something billions of light years away, we're not seeing the universe as it is, we're seeing the universe as it was. And this eruption is one of the most dramatic time capsules we've ever found. The light that reached our telescopes began its voyage when the universe was younger, denser, and far more chaotic. Galaxies back then were growing rapidly. Stars were forming at breakneck speeds. Black holes were expanding, merging, swallowing matter at astonishing rates. The cosmos was in the thick of its adolescence, a turbulent, fiery era where extreme events were not exceptions, but norms. To observe an eruption from this period is to glimpse a crucial stage in cosmic evolution. The galaxy we see in that distant light may not exist anymore in the same form. Its spiral arms may have shifted, its stars have aged, its black hole has grown. Entire clusters of stars might have formed in the wake of the eruption, lived full lifetimes, and died in supernova explosions, all while their light has yet to reach us. This is the paradox of deep time. The farther we look, the younger the universe appears, even as everything we see has already lived its life by the time we observe it. The eruption, frozen in time from our perspective, is a snapshot of a moment long gone. The bubble still appears to be expanding because its last visible stage is only now reaching us. The jet seems freshly carved, its shock waves still energetic, because we are witnessing the imprint of those forces exactly as they were billions of years ago. To the galaxy itself, the eruption is ancient history. The shock wave may have dissipated. The bubble may have stretched thin and faded. The black hole may have returned to a quiet state. Entire generations of stars could have formed from the compressed gas shells the eruption created. Civilizations, if they ever evolved there, may have risen and fallen long after the blast ended. From Earth, the event seems present, but in cosmic terms, it's a relic. This distance in time also adds a layer of complexity to our understanding. When astronomers analyze the eruption's brightness, its structure, its energy output, they must account for billions of years of cosmic expansion. Space itself stretched the wavelengths of the eruption's light, cooling and weakening them. The radio emissions we detect today are long, softened echoes of the original blast. The X-rays arriving now have far less energy than the ones that first burst from the galaxy. Even so, the eruption's intensity remains unmistakable. Even diluted by the universe's expansion, the brightness is extraordinary. That tells us just how violent the original event must have been, so powerful that its signatures survived a cosmic journey of unimaginable scale. The fact that we captured this eruption at all is a triumph of timing. If the galaxy's orientation had been slightly different, if dust had obscured the jet, if the blast had occurred in a region of the universe too congested for clear signals, we might never have known it happened. Countless other eruptions may be happening right now, hidden behind clouds of dust or oriented in directions where we cannot see them. Every detection is a stroke of cosmic luck. That's what makes this eruption such a profound gift. It lets us peer into the deep past and witness a moment that shaped a galaxy long before our own story began. It allows humanity, tiny beings in a small solar system orbiting an ordinary star, to look backward in time at forces so enormous they defy imagination. And it reminds us of something essential. Observing the universe is not just about looking outward, it's about looking backward, into eras that no longer exist, into moments frozen in ancient light. When we study events like this, we study history on the grandest scale imaginable. We study the universe as it builds itself, tears itself apart, and rebuilds again. And through that lens, we learn not just about distant galaxies, but about our own origins. Because every atom in our bodies was forged through the same cosmic violence we now observe from afar. This eruption didn't just expand our understanding of black holes, it reshaped the roadmap for the future of astronomy. It opened new questions, exposed gaps in long-trusted models, and revealed cosmic mechanisms far more dynamic and unpredictable than scientists once imagined. Events like this force astronomy into a new era, one where we must rethink how we observe the universe, how we interpret ancient light, and how we build the next generation of telescopes capable of capturing the most extreme phenomena nature can unleash. The first major shift is in how scientists now view black hole growth. Before this discovery, the prevailing theory suggested that black holes grew steadily, fed by slow, continuous accretion interrupted occasionally by short, intense bursts. But this eruption showed that black holes can enter prolonged states of hyper-efficient feeding, states that might dramatically accelerate their growth. If these states happen more often than expected, many supermassive black holes may have reached their enormous sizes far faster than previously believed. That forces scientists to rewrite parts of cosmic history. Galaxies in the early universe may have grown under the influence of black holes far more active than anyone realized. Some of the earliest quasars, those brilliant beacons visible across the cosmos, might owe their existence to eruptions exactly like this one. Understanding how and when these feeding frenzies happen could unlock answers to one of astronomy's biggest questions: how black holes at the dawn of the universe grew so massive so quickly. The second shift involves jet physics. The jet in this eruption behaved in ways no simulation had predicted. Its stability, its power, its longevity, everything about it pushed the limits of current models. To study jets like this, astronomers now need more sensitive instruments, especially in radio and X-ray wavelengths, where jets reveal their hidden structure. Existing arrays can map the bubble, but they can't fully resolve what's happening near the event horizon. That's why this eruption has become a rallying point for new technology. Projects like the Next Generation Event Horizon Telescope, the Square Kilometer Array, and advanced X-ray observatories will be able to peer closer to black hole jets than ever before. They could reveal the intricate interactions between magnetic fields and plasma that allow jets to remain stable. They could capture eruptions in real time, watching as they strengthen, collapse, and rebuild. They could show us whether events as powerful as this one are rare, or if the universe is filled with eruptions we've simply been unable to detect. The third shift is perhaps the most unexpected. This eruption has changed how scientists search for galactic archaeology. The bubble carved by the jet leaves a structural footprint that can last hundreds of millions of years. That means other galaxies might carry similar relics: massive cavities, disrupted magnetic fields, regions of odd star formation that hint at ancient eruptions long faded from view. With what we now know, astronomers can scour the skies for galaxies showing the same asymmetries, the same cavities, the same ghostly signatures of past activity. What once looked like random gas structures may now be recognized as the echoes of colossal eruptions. This redefines how scientists interpret galactic evolution and the role black holes play in shaping their environments. And finally, the eruption has sparked new interest in multi-messenger astronomy. These extreme events don't just emit light, they send out particles, neutrinos, and possibly even gravitational waves if the eruption was triggered by a stellar disruption. If a similar event happened closer to Earth, modern detectors might capture all these signals at once, revealing a complete picture of how black holes behave during feeding frenzies. It's a future where astronomy becomes more interconnected, where radio telescopes, X-ray observatories, neutrino detectors, and gravitational wave observatories work together to decode cosmic violence with unprecedented clarity. But beyond the technological revolution, there's something deeper happening. Events like this shift astronomy from being a science built purely on observation to one driven by prediction and revision. Every new discovery like this forces us to rebuild our models, reevaluate our assumptions, and embrace the messy, unpredictable nature of the universe. The eruption wasn't just a record-breaking flash of light, it was a turning point, one that tells astronomers they must look farther, dig deeper, and think bigger. It proved that the universe still holds secrets powerful enough to rewrite our textbooks in a single burst of radiation. And in the years ahead, as our instruments sharpen and our models evolve, we may discover that eruptions like this are not rare exceptions, but key chapters in the cosmic story we are only beginning to understand. Every discovery in astronomy changes our relationship with the universe, but some discoveries do more. They shift our place within it. This eruption, brighter than 10 trillion suns, reaching us across billions of years, is one of those discoveries. It reminds us that we are observers, living in the aftermath of ancient cosmic violence, trying to piece together a story that began long before our world even existed. To stand on Earth and detect an event like this is to realize how deeply connected we are to the cosmos. We exist because the universe is capable of extremes. Extreme pressure that forged atoms and dying stars, extreme heat that shaped galaxies, extreme eruptions, like this one, that redistributed the raw materials of creation. Without that violence, there would be no carbon in our cells, no iron in our blood, no planets to stand on, no stars to light our sky. We are, quite literally, the byproduct of cosmic chaos. This eruption becomes a reminder that the universe is not a peaceful void. It is active, turbulent, creative, destructive, and constantly evolving. From our small perspective, the night sky looks calm, stars twinkle, galaxies glide silently across the darkness. But that serenity is an illusion, born of distance. Behind it lies a universe roaring with energy, stars collapsing, galaxies colliding, black holes awakening. Yet, even in that chaos, there is order, there are patterns, there is structure. Events unfold according to laws we can study, understand, and predict. The cosmos is violent, but not random. It is dynamic, but not chaotic in the human sense. Its greatest eruptions follow rules that we uncover one discovery at a time. This eruption was one such revelation. It forced us to confront the limits of our knowledge, the places where our models fail, the mysteries we still cannot explain. It taught us humility. For all our telescopes, satellites, simulations, and theories, the universe remains far more complex than our understanding of it. Every new observation opens 10 new questions. Every explanation leads to deeper puzzles. There is a profound beauty in that uncertainty. It means discovery is never finished. It means the universe has more to teach us. It means humanity, for all our progress, is still taking its first steps into understanding the cosmos. And then there's the personal perspective, the human perspective. It's easy to feel small when contemplating an eruption that outshines trillions of suns. Easy to feel insignificant when imagining jets carving millions of light years, shockwaves reshaping galaxies, black holes swallowing stars with ease. But small does not mean irrelevant. We are the only known species capable of observing these events, of decoding their meanings, of weaving them into a narrative that stretches across time and space. In a universe filled with violence, we are the witnesses, the storytellers, the interpreters of cosmic memory. Our telescopes are our eyes, Our equations are our language. Our curiosity is our compass, guiding us deeper into the unknown. And every time we look up at the night sky, we are reaching across billions of years to learn from events that shaped the universe long before we arrived. This eruption reminds us of our connection to that greater story. It calls us to keep exploring, to keep questioning, to keep expanding the limits of what we think is possible. Because somewhere out there, even now, another black hole might be awakening. Another star might be drifting too close. Another jet might be carving a bubble through interstellar gas. And its light, carrying a message written in energy and time, is already on its way toward our small world. Someday, billions of years from now, another civilization, if any exist, may look back at the Milky Way and detect echoes of our own galaxy's violent past. They may study the remnants of an eruption from Sagittarius A, long faded but still traceable. They may learn from our galaxy what we have learned from distant ones. In that sense, the universe is a chain of observers learning from ancient light, each generation discovering the history left behind by stars, galaxies, and black holes that lived and died long before their time. This eruption is one chapter in that endless cosmic exchange. And as long as we keep observing, keep listening, keep searching, we will continue adding new chapters to a story far bigger than ourselves, one written across the sky, carried on beams of ancient light, and unfolding across the vastness of space-time.
Please subscribe and leave a like if you enjoyed this video. We hope to see you again soon for another session from Wisdom Sleepers.